Hello, good morning. This is Gavin, and today we'll be talking about the Archimedean property of real numbers. Last time we were discussing the concept of the density. What does it mean by the rational numbers that are dense in real? And today, the new concept of the new property is going hand in hand with the concept that we learned last time. We're trying to establish these two theorems regarding the distribution among the real numbers of the integers and the rational numbers. So Archimedean property is stated in this way. We know the following two equivalent properties both hold. So number one is for any positive number c, for all positive number c, there is the natural number, and we call it n, that is natural number, such that n is greater than c. It's quite easy to understand because we intuitionally understand that there are unlimited numbers that exist in a world. So no matter how we choose a number, we can always find another number bigger than that, or specifically natural number bigger than that, because natural number can go higher and higher. But we might never mathematically stated this before. So now this is a very logical way for us to say it. And we have the second statement that is equivalent to this one, is for every positive number. This time let's call this b, that is greater than 0. And we know that there exists another natural number n, such that 1 over n is smaller than b. It also makes sense, and I'll explain to you later. Such that we say 1 over n smaller than b. So, do you know how to prove it? We took it for granted before, but when we're actually looking at these two statements, if we want to prove it logically using what we had learned before or techniques like proof by contradiction, it might not be very easy, even though we know it's true. So how can we start proving? First of all, let us observe that both two properties are equivalent. Indeed, for two positive numbers c and b, they're related by b equals to 1 over c, right? This is their relation. And because for natural number n, for some natural number n, we know that n is greater than c if and only if 1 over n is smaller than b, right? This is true. Therefore, we know statement 1 and statement 2 holds together if one of them hold. So now let's prove one of them. Let's prove first one. Alright. By proof by contradiction, we know we have to assume the opposite. So we assume that this property does not hold unless derive a contradiction. So assume for the sake of contradiction, that 1 is not holding. So suppose there is a positive number c. Suppose there is the positive number c greater than 0, for which such that there is no natural number greater than c. We can use the positive axioms, and we can conclude that obviously n is smaller or equals to c for every single natural number n, right? And because the set of natural number is bounded above, given by this expression is bounded above, and we have learned in the first chapter or 1.1 section that the completeness axiom asserts that n natural number, the set of natural number, has the least upper bound, right? It is given by completeness axiom. And we just denote the least upper bound n by b, least upper bound. We denote it by b. And because b is smallest upper bound for n, and we know the number b minus 1 over 2 is for sure not an upper bound. Because b is the least upper bound already, and thus we can choose a natural number n such that there is some n such that b minus such that n is greater than b minus 1 over 2. And therefore, we know with plus 1 on both sides, we get n plus 1 is greater than b minus 1/2 plus 1. And it is for sure greater than b because after we simplify this expression, we get b plus 1/2. And then b plus 1/2 is for sure greater than b. And you see what we got? We got n plus 1 is greater than b. And n plus 1 is a natural number that is larger than b. And this is contradicting with our hypothesis or our assumption that the choice of b is the upper bound of n. It contradicts with the fact that b is an upper bound. And because we derive the contradiction, we know that in this case, our assumption for sake of contradiction is not true, which means there is no natural number greater than c is not true. Therefore, there must be a natural number greater than c. And since we already proved the first statement, and we know we already proved this statement, and we know first statement and second statement, they go hand in hand because they're equivalent. So we automatically know that second statement is true as well. Alright, we're done. Thank you for listening.